All right, let's kick this off. Today, we're doing a full technical post-mortem on a system that's absolutely critical to modern infrastructure, the distributed cache. We're going to tear down the architectural blueprint piece by piece and really scrutinize every single design choice, just like we were the original engineers on the project.
Okay, so here's the blueprint. The requirements are, well, they're intense. The system has to survive not just peak load, but also things like power outages. So as we go through this, remember the stakes are incredibly high. Every single design choice we look at has to be bulletproof against these failure scenarios. Let's dive in.
So here's how we're going to tackle this. We'll start at the very bottom, the foundation, why RAM. Then we'll zoom into a single cache node. After that, it's all about how these nodes coordinate in a cluster, how we scale with consistent hashing, the classic trade-off between availability and consistency, and finally, how we manage the data lifecycle. A solid plan.
Okay, first up, the foundation. Why RAM? Look, you have to start with the hardware, right? For a cache, your choice of storage is pretty much going to define its entire performance profile. So let's answer that fundamental question. Why RAM?
And this table really tells the whole story. You've got this fundamental trade-off, right? On one end of the spectrum, you have CPU registers. I mean, they're blazing fast, but you can't store anything in them. On the complete opposite end, magnetic disks give you tons of cheap capacity, but they are just painfully slow. And right there in the middle is our sweet spot, RAM. It's built on commodity hardware, so it gives us that perfect balance of high speed, decent capacity, and a cost that actually works at scale. This is it. This is our building block.
All right, so we've settled on RAM. Now let's crack open one of these cache servers, a single node, and see what's going on inside. The big question is, how do we actually structure the data in memory to get the speed and efficiency we need?
So here's the challenge, and it's really a two-parter. First, we have to find any piece of data instantly. We're talking O of 1, constant time lookups. But second, RAM isn't infinite. We're going to run out of space, so we need a really smart way to decide what gets kicked out. Fast lookups and smart eviction. That's the game. So for that speed problem, the answer is a hash table. It's the classic data structure for this, giving us that beautiful O of 1 average case lookup. You just hand it a key, it does a quick calculation, and bam, it knows exactly where your value is stored in memory. There's no searching, no scanning, just pure speed.
But here's the catch. The hash table is fast, but it's also kinda dumb. It has no idea which data you used a second ago versus an hour ago. For that, we need another data structure to help out. And that's where the doubly linked list comes in. It's fantastic for keeping things in a specific order and letting us move items around with almost no effort. And this is how the magic happens. The two work together. The hash map gives you that instant O of 1 lookup. It finds the key and gives you a pointer directly to a node inside the linked list. Now, whenever we access that data, we take that node and, whoop, move it right to the front of the list. It's an incredibly elegant solution. This simple move keeps a perfectly sorted list from most recently used to least recently used. And that gives us our eviction policy, LRU, least recently used, problem solved.
Okay, so we've got a single node nailed down. It's fast, it's efficient, but one node doesn't make a distributed cache, so now we have to talk about coordinating the whole cluster. How do all these individual servers talk to each other? How do clients know who's who? This, my friends, is a classic, thorny, distributed systems problem.
You can really see the evolution of thinking here. I mean, you could start with the simplest thing, static config files on every client. But that's just a nightmare to manage, a total deployment headache. So, okay, step 2, a centralized config file. A little better, sure, but it's still a manual process. And now you've created a single point of failure. The real production-grade answer is the third option, a dynamic configuration service. We're talking about tools like Zookeeper or etcd. These things automatically watch the health of the cluster and just push updates out to clients. Yeah, it's more complex to set up, but for high availability, you absolutely have to do it.
All right, now for the big one, scaling with consistent hashing. Honestly, this is probably the make or break challenge for any distributed system. How do you grow this thing? How do you add more servers when traffic spikes or remove them when it's quiet without the whole system just collapsing?
So let me paint you a picture of what can go wrong. It's the absolute nightmare scenario. If you just use a simple hashing function, like a modulo, the second you add one new server to the cluster, boom. The location for almost every single key changes. This causes what we call a catastrophic data reshuffle. The cache becomes useless, and every request hammers your main database. It's a total meltdown. We have to avoid that at all costs.
And this is where consistent hashing comes in to save the day.
It's a brilliant technique. Instead of everything getting remapped, consistent hashing guarantees that when you add or remove a server, only a tiny fraction of your keys need to be moved. It's what makes elastic scaling possible. It's the absolute linchpin of this design.
And let's talk performance, because that's what it's all about. With consistent hashing, a client can figure out which of the end servers holds the data it needs with O of log n complexity. What that means is, even if your cluster grows from 10 servers to 10,000 servers, the time it takes to find the right one barely increases. That is absolutely critical for keeping latency down as you scale.
Okay, now we get to the heart of almost every debate in distributed systems: availability versus consistency. You can think of it like this. Do you want an answer right now, even if it might be slightly out of date? Or are you willing to wait for an answer that's guaranteed to be correct? Getting this balance right is one of the toughest parts of the job.
So, on the one hand, you could have a single server for each chunk of data, what we call a shard. The problem, that server becomes a single point of failure. If it goes down, all that data is just gone, unavailable. So the better, more standard approach is a primary-secondary model. You create replicas. This gives you high availability. If the primary fails, no big deal, one of the secondaries just steps up and takes over. Plus, you get a bonus. You can use those replicas to handle read traffic, which is a lifesaver for hot shards, those pieces of data that get hammered with requests.
Of course, having replicas introduces its own problem. How do you keep them all in sync? For replicas that are sitting right next to each other, say in the same data center, the answer is synchronous replication. This is non-negotiable. It means when a write comes in, the primary node doesn't just say, "Okay, got it, back to the client." No, it waits. It makes sure every secondary has successfully written the data, gets that confirmation, and only then does it tell the client the write is complete. It's slower, for sure, but it's how you guarantee that no one ever reads stale data. Strong consistency.
Okay, we're in the home stretch. The last big piece of the puzzle is managing the data lifecycle. We've built this massive, scalable system. Now, how do we handle the data inside it? We need to have rock-solid policies for what data stays, what goes, and when.
And we really have three main tools in our toolbox for this. First, we've got our eviction policy, LRU, which kicks in when the cache is totally full. It just removes the least recently used item. Simple. Second, we have time to live, or TTL. This is great for data that you know will become stale. You just set a timer on it, and it automatically disappears. And third, you need a way to do it yourself. A manual explicit delete API.
And this quote right here explains exactly why that delete API isn't just a nice to have, it's absolutely critical. Think about it. A user deletes their account. Your code correctly removes them from the main database. But if you forget to also delete them from the cache, well, for the next few minutes or hours, your system might still think that user exists. You're serving stale, wrong, potentially dangerous data. To keep your cache and your database consistent, you have to have that explicit delete.
So look, the design is solid, the blueprint holds up. But let's end on a real-world question here. You're looking at this entire system, everything from the client library, the network, the config service, the cache nodes themselves. When the pressure is on, when peak load really hits, what breaks first? Where does that first crack appear? Think about it. That's the kind of question that really separates a design on paper from a system that survives in production. It's what keeps us engineers up at night.